5, 6 feet, 5 feet. So yeah, so that.
Okay, so people are coming back from the exhibit lunch break, and we're going to get started here with the talk by William Setterberg about CubeSats.
Should we wait a couple minutes or should we just?
Let's go.
All right. Yes. Should I turn my video on? Or?
You should, because yeah, they'll be able to see the entire room. Those were remote.
Oh, yeah, the remote video is.
Okay.
What about start video right there?
This is my computer.
That's not what you want.
We could have the room with the camera there and then there's a camera here.
Oh, okay.
This is, let's just say that. All right, so. Yeah, my name is William. I'm a third year physics PhD student here at Minnesota, and I work on this CubeSat project called Impress. So I'm going to be talking about that today. I want to say thanks to Demos and James for extending the offer to talk here, and I hope you all find this interesting. Right, so we're going to talk about CubeSats and click. All right, so here's an outline of the talk. I'm going to talk for a good chunk about solar physics and solar flares, because I figure not everyone's up to speed with that, and it's interesting stuff. And then I'll talk about the science that it's trying to achieve, this CubeSat, what it's trying to achieve. And then I'm going to talk about the small sat lab here at the University of Minnesota, how it's organized and what we're working on right now. So start with the first slide about background. Maybe I'm kind of preaching to the choir here, but space isn't empty. We talk about it like it's this kind of void and vacuum, but there's a lot of stuff that's out in space, especially stuff coming from the sun. So like one thing that's called out here is, can y'all see my cursor?
Mm-hmm.
Yeah, it's the solar wind. So it's this stream, this fluid of electrons and protons and other particles and magnetic field that flows out from the sun out into interplanetary space, and it interacts with the Earth's magnetic field. There are also other space or solar events, like something that's shown here called a coronal mass ejection, which is where the sun ejects a big blob of plasma out into interplanetary space, and those are often accompanied by solar flares, which I'll talk more about on the next slide. Also in space, we have a lot of observatories, space-based observatories that look at light. And by light, I mean visible light through gamma rays. They look at light and particles that come from the sun. And I have this one in particular here circled. RESI was an X-ray space-based telescope that was active for about 20 years. And so that's, I mostly study X-rays, so RESI is important to my, I guess, the fundamentals of that field. Another thing called out here is the Van Allen probe. So those aren't solar satellites, but they studied the radiation belts around Earth. So the radiation belts are high energy particles that are trapped in the Earth's magnetic field. And one of the PIs, one of the principal investigators for an instrument on those probes was actually at the University of Minnesota. So it's an interesting fact. And something that's not in this NASA graphic is that actually there's hundreds of other kinds of satellites that make things like cell phones and the internet and GPS work. And those all get influenced by solar activity. So understanding what's going on the sun is important for our everyday lives in that way. So I said I was going to talk about solar flares. So this is just a movie of a solar flare later, and it'll should loop here. So this is a relatively bright solar flare occurring off the limb of the sun, and it's accompanied by a coronal mass ejection. So this is taken over a period of about 3 hours, 11 to 2, last April, almost a year ago. And I want to point out a few things here. So one is that there are these loopy bright structures here. Those are actually magnetic field loops that are filled with hot plasma that you can see in this extreme ultraviolet movie. And another thing I want to point out is the scale here. So the Earth is, the diameter of the Earth is like 1/100th the diameter of the sun. So, I mean, if you put Earth right next to the sun, we would just be completely engulfed by these solar flares and these magnetic loops. So these are huge events. They're extremely energetic, and they're really beautiful. So that's kind of observationally what a solar flare is. It's these things that we can see on the sun. It's these, they're often accompanied by coronal mass ejections. You just hide the zoom controls here if I can. So more technically, a solar flare, it's an impulsive release of solar magnetic energy. So the way this happens is, I mean, the sun's magnetic field is really complex and it's all twisted up. And as that field twists and pieces of it move around on the surface of the sun, it builds up shear or magnetic tension in these loops that you can see on the surface. And eventually it becomes energetically favorable for those loops to reconfigure through a process called magnetic reconnection. And that releases tons of energy. I mean, it releases like billion nuclear bombs worth of energy over the course of minutes to hours. So solar flares are driven by magnetic reconnection. And then we can observe emission from solar flares across the electromagnetic spectrum. But in particular, we can look at emission from energetic particles, and that emission is X-rays. And so some of the X-rays come from just really hot, like tens of millions of degrees plasma, and some of them come from particles that are accelerated through non-thermal means. So I've mentioned coronal mass ejections, just to put it into a context a little bit. So there was this event in 1859 called the Carrington event. And what actually happened is there was a massive coronal mass ejection that probably coronal mass ejection that hit the Earth and caused a really strong geomagnetic storm. It actually lit up telegraph lines when they weren't connected to anything, and stuff caught on fire. So these solar events, again, they can really influence everyday life. I mean, imagine what would happen now if we weren't prepared for something like that. We'd be toast. So.
No pun intended. Pun intended or no pun intended?
Is there something wrong with toast?
No, it's gonna be fried.
We wouldn't be, no, our cell phones would be fried. Yeah. Yeah, that's, okay, well, toast. Yeah, so I mentioned, so there's a few different ways that you can get X-ray emission from the sun. One of them is through these non-thermal particles. So I just kind of zeroing in on the research here, but let's focus on the path of non-thermal electrons and what they do during a solar flare. So I mentioned solar flare is due to magnetic reconnection up in the corona, where you have magnetic field lines reconfiguring, releasing energy, and the corona is relatively low density. So you can get particles accelerated up there, and they don't hit anything because it's low density. And they will spiral down the magnetic field lines here because they're charged and they obey the Lorentz force law. They'll spiral down the field lines, and eventually they'll hit a higher density region of the sun, the chromosphere. So it's about 1 million times as dense as the corona. And when they hit that higher density atmosphere, they emit X-rays via bremsstrahlung, which is a result of the particles giving up energy to nuclei. So they emit X-rays of energies of like tens to hundreds of kiloelectron volts. And then as the flare progresses over minutes and hours, some of that chromospheric plasma heats up and actually goes up into the loops. And we saw that on that extreme ultraviolet movie a little bit, and you just get hot plasma that emits thermal X-rays. So this is kind of the standard flare model. It's pretty well established that this goes on, but it's actually not maybe as clear cut as that. So there definitely are non-thermal particles in solar flares. You get these accelerated particles because, you know, there's one strong piece of evidence is this study from the 1980s where they found really short timescale variations in hard X-ray flux they were just too fast to be from some kind of thermal emission. I mean, it's just things can't heat up or cool down fast enough to explain those fast variations. But there are still open questions about how these electrons are actually accelerated. I mean, there's different ways that they can accelerate. So you could have just have an electric field that literally just pushes electrons and other particles along the magnetic field loops. Or you could have magnetic shock waves that kind of bounce the particles back and forth, or maybe the particles get trapped around a shock front as they are propagating down. And that's one way the particles can get energized. Or you could have plasma waves, like alphane waves, exchanging energy with the electrons in the magnetic field loops. So there's ways that can happen, and it's also not obvious where these electrons get energized, and could happen up by the reconnection site. That's kind of the classic picture, or it could happen closer to the loop foot points. And it's in the title. I probably should just say it though. We care about this because something like half of that billion nuclear bombs of energy goes into accelerating these electrons. So that's why we care about this portion of the solar flare. Yeah, it's probably a mix of everything. So it's a hard question to answer, you know, how are particles actually accelerated during flares? But I'm going to talk about one way that we can try to probe that, and that is using photon timing. So we're going to look at, this is basically a case study with flare from August 2011. So this is some work published by a previous UMN grad student. So let's start off with the AIA image here. So this is a extreme ultraviolet image, again, the same wavelength that was shown in the movie before. And that's kind of where the flare is actually happening. So you can see, I wish I could zoom in. Yeah, but there are, you know, magnetic loops here. It's pretty complex and twisted around. But the AIA is on has an exposure time of like 12 seconds, or a cadence of about 12 seconds. So it's hard to track short time scale things. So I also mentioned RESI earlier, which is the solar hard X-ray telescope. And so you can take pictures of X-rays. It's hard to do, but you can do it. RESI basically took a Fourier transform of the sky, and then you do an inverse Fourier transform to make the image. And this is useful. I mean, the red stuff here is lower energy, so probably thermal X-rays. The blue stuff here is higher energy, probably non-thermal. And so it shows that those two types of emission are spatially distinct, which is kind of in line with that standard flare model. You'd expect them to be in different spots. But you have to image for a few seconds, so it's not as useful for doing timing studies. Another type of data you can look at is time series data. So this is from the Fermi Gamma Ray Burst Monitor, which is an astrophysics instrument that's supposed to look for gamma ray bursts. But you can also use it to look at solar flares. So that's what this student did. And he basically took a moving average of the data and then subtracted it off, and then was able to quantify which variations are statistically important or significant. And then looking at the timescales of those variations, you can actually learn or constrain some of what's going on. So the shortest timescales that you observe have to be explainable. So you can use that to reject some kinds of acceleration mechanisms depending on the geometry of your flares. And so that's one thing you can do. You can also look at how the time of arrival of X-rays to Earth depends on the energy. So imagine you have a flare loop and you have all of these electrons that get, see if you can see it on Zoom, not really. Well, if you get a certain kind of time delay between X-rays arriving at Earth, that could be an indicator that particles are accelerated in a spatially localized way. So that's one thing you can do. And you can take these timescales and use them as model inputs because you can come up with a great model for what's going on in a solar flare, but it doesn't line up with reality, then it's kind of garbage. But you need to have something to compare with. So that's another use for these kinds of timing studies. So now that actually brings me to IMPRESS. So what we're trying to do with IMPRESS is measure X-rays fast. The acronym stands for the Impulsive Phase Rapid Energetic Solar Spectrometer. So we're going to measure X-rays from accelerated particles during solar flares. We're also going to measure X-rays from thermal plasma, but that's not the main science focus. So it's a 3U CubeSat. And yeah, this is an old render, so I know I was going to get some flack for that. So I put a preemptive message up.
It's all right.
So it's, I don't know if you all saw the Socrates engineering model downstairs, but I mean, it's this big bread box or bread loaf size, small CubeSat. And we're building it in collaboration with a few different institutions. So the University of Minnesota is the PI institution, or
We're the lead.
we're the lead. So yeah, I mean, we're doing the bulk of the work and responsible for the spacecraft bus here. I think that's the right term, just a scientist. But, so we're doing this bottom 2U, which has all of the supporting equipment like battery and attitude control and that sort of thing. And then the top 1U is the hardware is being assembled by some folks at Montana State University. Of course, they had input from Minnesota, but they're responsible for assembling the hardware. And then we've also got collaborators, someone at the University of California, Santa Cruz, who's helping us with a lot of the detectors details, and someone out of Boulder, Colorado at Southwest Research Institute who's helping with different kind of detector details. So it's a collaborative effort, and we're working on it. Right, so this is just some more details about sort of science requirements for a detector. So what we're actually trying to do here, I mentioned we're going to try to do these timing studies on X-rays from solar flares. So in order to make that useful, we need to have some kind of energy resolution. So we need to be able to tell a photon of one energy apart from another energy. So we have actually pretty lax requirements. It's 80% peak width divided by the mean at 20 keV. So that's pretty lax, but it's enough to achieve our science. We're going to have 30 millisecond exposure times for these X-ray detectors. So, or time bins is another term. We're going to basically take snapshots of X-rays, but sum them up over 30 milliseconds in time consecutively. And so that's the sort of data we'll be taking with IMPRESS. And we're also trying to measure dim through bright flares. And so I don't really quantify this here. I can if you want me to, but we're going to put different thickness aluminum windows in front of these 4 individual detectors. And so each one will be sort of optimized for different flare brightnesses. So if you have a dim flare, you might pick it up on one detector and not others. And if you have a really bright flare, some of them might saturate, but you'll still be able to get some useful data out of at least one detector. Yeah, so so those are the requirements that were set for this instrument a while back. We're doing our best to meet the requirements. And as part of that, we have these weekly meetings between institutions. So people from Montana join, people from Boulder join, Southwest Research Institute, and we talk about updates with the detector, updates with the mechanical interfacing between Minnesota and the detector, or if we have electrical questions, we can get them answered, like how is this cable going to fit? Do we have too many wires? Things like that. So those are really useful meetings. And I just kind of threw this up there, but we've got detector simulations too. So, the data that we measure isn't just going to be like exactly, yeah, we measured this X-ray, this energy this time. We'll need to kind of do some inversion to get the actual photon spectrum back from the instrument. response. So I've done some modeling, actually using the same software that CERN uses for their high energy detectors. So it's kind of interesting, but that's a different story. I'm going to keep talking about the detector because that's kind of what I do. So we're trying to get an engineering model from Montana at the end of April. That's the new goal. We've been waiting on this thing for a while now, but I think we can actually get the engineering model. So it's just going to be one of these scintillator detectors and one of these readout electronics boards in the actual 1U enclosure that we need. So we'll be able to start doing sort of real testing with that and see if things fit together, see what needs to change. And then at Minnesota, we've been running efficiency testing. So that's just characterizing, okay, what percentage of photons does the detector actually pick up? Which is actually harder than you might think, because you have to first know how many photons are hitting the detector, but then to do that, you need another calibrated detector. But to do that, you need another calibrated detector. So it's harder than you'd think, but that's something we've been working on. We've been looking at how temperature changes our response, so that can shift basically scale the energy gain that we have, and it also increases noise. Just something that we need to look more into. And then we've been thinking about pilot projection. If you have two X-rays incident at the same time, those photons can be recognized as basically one event and summed together by the electronics. That's not good, because it's two photons, it's not one photon. So you end up with erroneous data. And we've been talking to the different detectors. So we've got two commercial components here. So we've got the silicon-based detector, this Amtech detector, which is basically COTS, and we just put it in, and it commercial off-the-shelf COTS. We just put it in, and it's supposed to work. It works pretty well so far. And then we've got commercial electronics that we're connecting to custom detectors and custom readout. Okay, one last detector slide. So we've had some undergrads contribute to detector development with their senior theses a lot. So this is from someone who graduated last fall. He presented at the American Geophysical Union conference. So this was simulating a solar flare energy spectrum. So units are kind of weird, but it's basically photons versus energy. So simulate the spectrum, pass it through the instrument response, and then try to perform a fit on that simulated data. And his results worked really well, which maybe is obvious because we knew what was going in, but so this was good practice, like working with the software and the data products that we'll actually have on orbit. And then I already mentioned this, but we're doing efficiency testing and then some anti-coincidence stuff right now. Another thing I want to point out is that it's not just the detector team in Minnesota. There's a lot of sub teams that do a lot of really interesting work here, and learn a lot about more than just science, at least from what I've seen so far. I mean, team. So we basically have a couple of different teams, and they're not really like tiered, like waterfall flow down, even though that's what the diagram looks like. I think of it as more of like a communication between teams sort of setup. But the team leads here we meet with them once a week, and they get to learn a lot of leadership skills, like how do you delegate work to people and not just do everything yourself? Because that's a hard skill to develop. It's like, how do you give someone a project that they can actually tackle without just giving them too much or too little. So that's one aspect that people get to learn about. And then we've got two project managers, one for Impress and then one for a related CubeSat that uses the same hardware, and they keep us on track. I don't know they're here right now. No, they're not. But yeah, also a really difficult thing to do. Really grateful that they're on the project. Chief engineers, they kind of think through mission-wide engineering plans, is how I phrased it, but they're kind of on top of the engineering side of things. And then we have weekly meetings between so Demos, who's one of the PIs, and then Lindsay, who's my advisor, and then I'm the project scientist and all of the team leads. We meet once a week. We see how people are doing. We talk about recent progress, and we recently we've been acting on feedback from a design review, which has been yeah, we got some intense feedback, and it's good. We did. So this is just sort of sub-team status here. There's a lot of stuff going on. I figured I might as well just go over it because I have some slides specific to each sub-team, but I'm just going to give a summary first. So the attitude control system, attitude is where the spacecraft is pointing, how it's oriented, where it's located in space. So they're working on some things they're working on are integrating new ADCS hardware, which I'll have a picture of in a second, figuring out the GPS and what we're going to use it for, which we've been trying to do for a while, but it's a complicated thing. And then also thinking about how to execute different plans for when we're on orbit. Sometimes we might want to, basically just point at the sun. Sometimes we might want to point somewhere else for calibration. Don't really know yet. So that's a pretty complicated thing, and they're working on that. Flight computer team, they're working on getting people and more sub-teams involved in software writing, because up till now it was pretty like everyone was off in their own little world working on stuff, but we're really having to integrate now. So that's been a difficult process. And we're also they're trying to think about, should we have everything in one program running on threads, or should we have multiple programs that communicate between each other? So that's another question that needs to be answered. Radio, we're thinking about error correction. We're thinking about how do we really need all the error correction that we've got, and then getting people up to speed on hardware testing, because some of it hasn't been done in a while. Detector I've talked about, so I'll skip. And then EPS, so electrical systems, they're going to take all of the components that we have and measure how much power they draw, because we need to know that. And we've been advised that SD cards fail a lot on orbit because they're really kind of unreliable. So we might try to add a second one. If anyone has any advice on how to add a second SD card and optionally boot from it, please let me know, because that has been keeping me up at night. Yeah, structures doing great. Keep pestering Montana because they're kind of slow to get back sometimes, but yeah, that's how it goes. And so the thermal team, I have a slide on that, so let's get that. And chief engineers, we need to figure out how the orbits are going to look. So nominal orbits and also atypical if something goes wrong. So now I've got some demo slides. So this is attitude control. Got some nice pictures. So this is the hardware system on the left that we're going to use basically to control where the spacecraft is pointing. These little boxes are called reaction wheels. So they are just heavy wheels that spin. And as they're spinning, they apply a torque to the spacecraft so you can reorient it in different ways. And then this is talking to part of that system using I²C. So that's working. And then we got this GPS dev kit so that we don't have to have like sketchy jumper wires going everywhere to power the thing. That was not fun. So thermal team this is a super simplified mesh of the CubeSat. You can see that they basically broke it down into large chunks, and so it makes simulations a lot faster, and it kind of makes them more meaningful because it's easier to digest what's going on, and then trying to figure out why some of these temperature gradients are so sharp. And you think this is the GPS or the flight computer here. It's at like 70 Celsius. Why is that so hot and not conducting heat out to the spacecraft body, which is at 15 C? So trying to figure out that sort of thing, and also making sure the detectors don't get too cold. Because that can make them stop working. Structures, I just want to throw up a view of basically the whole CubeSat here. So trying to figure out what we want to do with, they want to do with solar panels, and Kelly can correct me if I'm wrong, but do we want double-sided? That's more for exact, which is this other mission based on the same hardware. We want to figure out if we're going to keep the same solar array design or change it. And then at some point we need to start just machining stuff, putting it together. That's going to be quite the process. Oh, there's one more slide on detector that I can't resist. So this is a light type box from Montana. So scintillators, they convert X-rays into optical photons. So any sort of stray light is going to mess up your measurements. We really don't want that. So this box is sort of flight-like in that we're using the same or a similar PCB to what's going to be used in flight, same electronics, but it's not the 1U form factor that we want. It's just a box. So they were testing that over in Montana last December. And then this was a couple of months ago, testing out a harness or a connector to attach the detector board to the flight computer. And we sent that over to Montana for integration. One thing about the harness is that it includes an extra wire for pulse per second signal, and we're using pulse per second to synchronize all the detectors together. Yep, so that's all I had in terms of stuff here. Just to go over the main points again. So the sun is emitting photons and electrons and protons out into space, and they affect us. It's interesting to study that. And we're going to study it using this CubeSat called Impress. So we're going to do mostly timing studies with Impress. We can't take images, but we'll learn a lot about photon timing and acceleration in that way. And then the SmallSat team here at the university is big, and it's a lot of work. We're doing a lot of good work, and we work hard to work as a team. So here's some stats about CubeSat. We're hopefully delivering the end of this year, but every time I put these slides up, it seems to slip. So launch date 2020, maybe more realistic, deliver. So we hand off to one person, and then they wait a few months and hand it off to the rocket, and then it goes up, and it takes another few months. So maybe launch date 2024, maybe 2025. Mission lifetime probably going to be closer to 5 months because we'll be at a maximum of the solar activity cycle. And we need a minimum 3-month science phase. That's one of our requirements. So yeah, I'll stop there.
So we have lots of time for questions.
Why was cerium-3 bromide chosen as the
Yeah,
scintillating detector?
let me find a good picture. Okay, I'll just go here. So solar flares are, so the way the scintillators work is they count individual photons. At least in the perfect world, they would count individual X-rays. And we want them to count individual X-rays as often as possible and not get those coincidence events. They don't have an instantaneous time response to incident X-rays, the scintillators, I mean. And so we tried to, or predecessor chose cerium bromide because they are, it has a really short time constant. Something like 20 nanoseconds time constant. So you take that time constant, and then you have to like convolve it with all of the shaping that goes on in the electronics. You end up with like microsecond or some fraction of a microsecond that you get for a complete pulse. And from that, you can compute what average count rate you can handle, expecting like 5% coincidence events. So it's based on the speed And it's supposed to have good energy resolution because it's the number of optical photons that cerium bromide produces per incident KeV of energy is really high compared to other scintillators. But because we have these circular crystals and a square readout, we're having some issues with the energy resolution. So, but yeah, so it was timing and energy for the consideration, you know, sort of maybe didn't pan out as we'd hoped it would. Yeah, right.
Are these solar events, are they predictable or is the camera on all the time?
Yeah, that's a good question. So, that's a good question. Yeah, so the question is, are the solar events predictable, like solar flares and coronal mass ejections, or are these detectors on all the time? So we're going to be on all the time that we are in sunlight. You can predict solar flares with certain levels of confidence. And then there's different techniques for predicting them, like, okay, this month there will be 4 M-class flares, or today there's a 20% chance that you'll get an M-class flare. But there's not like, it's not like meteorology where you can, you know, forecast a week's worth of solar events. So we're going to be on pretty much all the time. So that's going to be, we're going to have to really restrict how much data we send back down to the ground also, because we're collecting too much to send all of it.
So you mentioned the solar event cycle, but apart from that, what do you use to determine the mission's lifetime?
Yeah. Let's see. I'll go back to the structures diagram. So I didn't determine it. We had grad student, master's student,
Alex.
work on this. Alex. So PhD student, yeah. So we basically took the orbital parameters that we had, which is basically start from the ISS at whatever altitude, I think it was 400 kilometers, and assume a relatively reasonable orbit, and then look at the drag coefficients, I think, depending on if we're in the solar panel, like cross direction, moving the RAM direction, or if we have just the side of the CubeSat, which is less surface area, and then did some sort of assumptions about orientation and orbit, and then we were able to, or Alex was able to compute orbital decay plots, which is basically like altitude versus time. So it ended up being, the bounds were about 5 months up to 8 months.
So just to add to that, so kind of what William kicked off, space is not empty. So there's actually drag on orbit. Yeah. So that's what's going to slow it down and bring it up. And the funny thing about IMPRESS, we want to look at the sun. More solar flares, great for the science, but there's going to be more drag and life's going to be shorter. So
Power is gonna be more.
yeah, but it's going to be a short orbit because when the sun injects all that stuff, there's a lot more drag up there.
Yeah, and like, just, yeah, when you have a geomagnetic storm or solar activity or something, the atmosphere literally heats up and expands further out into space. So that's part of the reason you get more drag, is there's more air up there. Yeah.
What happens when like your months are up? You just kind of, you just let it keep orbiting and just don't check on it anymore?
What do you mean when our months are up? Like when the
Like when you said like 5 to 8 months
Mhm.
is like your time frame.
Yeah.
3 months of science, like once that's over, like what do you do?
well, maybe I should have been more clear with that. So we need, I mean, we would like to have 3 months
Oh,
for science.
okay.
We can, I would love to keep taking measurements for longer than 3 months.
Sure.
But after 5 to 8 months, we're gonna re-enter the atmosphere.
Oh, it comes back.
We won't be able to go pick it up.
As that happens.
Oh,
It'll be crispy, it will be burnt.
Toast. And toast.
There are rules that say we have to burn it up without being toxic, so.
Yeah.
So no titanium. Cerium bromide is really dense. I don't know where that's gonna go, but they said it's okay.
They said it's okay.
Yeah.
So Impress and Exact are completely identical hardware wise, they just have different software because they have different science, correct? Or pretty close to identical hardware wise.
Yes,
So here's my real question, and that is, tell me about the pointing. For
yeah,
this one, you want to point at the sun.
Yep.
The other one, do you have to point at all? Tell us a little bit about the other mission.
but exact.
Exact.
I don't have any slides on that, but we might as well just stay here. So exact is looking at. So Demos is the expert on this. I'll do my best to summarize it, but it's gonna basically stare at the crab pulsar to validate a navigation algorithm based on pulsar emission. That's kind of it. So we're going to be staring mostly at the crab pulsar and other pulsars. The pointing for exact is a lot more complicated because we need to, at least with the way the solar panels are oriented here, they're facing the same way as the detectors. And so for Impress, it's really nice. If you stare at the sun, charge, win-win. For exact, if we want to look at the crab pulsar, you know, the sun could be here. I do this. The sun could be 12 o'clock and the crab could be 4 o'clock. And, you know, then if you want to look at the crab and do your science, you're not going to really be able to charge. So we're still thinking through that. That's something chief engineers need to figure out this amorphous. And, you know, we'll all be part of that conversation, but,
What about for telemetry? Do you need to repoint it, or your telemetry is completely isotropic?
nominally isotropic. We might need to repoint back, like, so the antenna, you can't quite see it here, but the radio antenna is right on the bottom of the spacecraft. And so we did some radiation, or someone did some radiation pattern testing. Found at least along one angular direction, it's pretty much isotropic. You're missing like a 50, 60 degree cone. So we might have to point a little bit to send data down to the ground, but it's not super beamed signal, but that's something to think about too. Yeah.
Pointing is gyros and magnetorquers, or just gyros?
Yes.
Yeah, we have both. So I don't think the magnetorquers are in this image, but
It's the second board down. The big silver bar right there is holding a circular magnetorquer.
the cube coil.
The cube.
That's
No,
what it's called.
that's the one below that. That's the
Oh.
orange one. It's the one right above it, the second board, the PCB.
Oh, got it. Yeah, so for attitude control, yeah, we've got the reaction wheels, and then to dump momentum, as they say, we have the magnetorquers to give up some of the angular momentum to the Earth's magnetic field.
Other questions? I've got more, but let's get more questions here.
Yeah, I love the questions. Thank you so much. I mean, I went a little fast, as I'm prone to do, so we've got plenty of time.
I think it's interesting and I know the answer, but I don't know if anybody else is curious about it.
Mhm.
How does it know that it's pointing at the Crab Nebula pulsar, and how does it know that it's pointing at the sun? Do you understand that part of it?
I know if we're pointing at the sun, we've been thinking a lot about, we have some sun sensors, and there's this camera that is a sun camera. As for pointing at the crab, I actually don't know what we're using. Oriented.
Can't you tell the sun just by the fact that your solar panels are doing better?
You can, I mean, that's basically what we have for some of it, is we have just photodiodes on really different axes of the satellite, and so it's like on, off. But that was something that had been discussed, was just use the solar panels as the sun sensor, and I don't know what the Kelly says no. I don't know what the reason for avoiding that was. But that's not what we're going with.
Okay, so now into the embarrassing part. What went wrong with
There's one
Socrates?
There's no, let's go on question.
Dodge that bullet.
Any better, but
Yeah.
it looks like you at the end sort of put the timeline and then
Yeah,
I think at some point today I've heard you're a grad student.
Yeah.
So right, like, and then like the timeline had shifted.
yeah.
So
He's
is
never
that,
grad.
is that impacts your life? Like that timeline shifting then also means your thesis is shifting?
Roughly? That's a good question. I mean, so my advisor is kind, and so I'm working on other projects too.
Okay.
So looking at real So let me go back to this constellation of oops, these are extra slides. Well, this is the sun sensor. Anyway, so I'm gonna go back way to the beginning here, actually, that constellation of satellites here. So I looked at data from RESI just for fun, even though it's decommissioned. It's coming down in a couple of months back into the atmosphere. I'm looking at data from Solar Orbiter. It has an X-ray telescope. I've looked at data from here. Actually, the images that I showed were from here, and then Keynote is a different X-ray telescope that does lower energy stuff. So I'm looking at, it's not just if the CubeSat doesn't work, I don't have a thesis, but I'd like to stick around to see it launch and take data. I mean, you know, the main thing is that it has this really nice timing that just you don't get all the time. So it'd be great to work with.
It's cool, especially to see like, you know, projects that have org charts and things. I was, you know, characters, so the org chart is very small. I understand.
Yeah, you want to, I'll pull that back up. The org chart, this one?
Yeah. So are there other project scientists on this, or you need this pretty much, right? Like the science is pretty much what you've been working on.
So there's Lindsay and Demos, they're the PIs, but then there's me working on Impress, and then there's Kyle working on Exact. So there's two of us, and then, I mean, the detector team folks definitely have, we talk with them about the science too, but the requirements, they were set a while back. So what happened with Socrates?
Well, you might not know exactly, but what's going to happen better with this one? Because Socrates didn't actually work quite well.
Mhm. Yeah, so there was a different CubeSat called Socrates that Minnesota worked on, and it never made contact with the ground, I think. So we just need more testing. We have a different battery. I believe that was thought to be an issue with Socrates, is the battery. So we have a different brand battery, and yeah, we just need to test as one of the Montana. Our colleague at Montana said, we're gonna have to test the heck out of this thing and just make sure that it works. I mean,
So what is it, for instance, that deploys the solar array? Is it a wire cutter? Is it something deteriorates in time? You know,
yeah,
something goes rotten on you, like really poor fishing line or something like that?
well, we do have poor fishing line. No, maybe not poor. We do have fishing line. So the panels are going to be tied down here, and there's a board, the burn wire board, that has nichrome wire. So it's like a high temperature wire, so it'll just melt the fishing line. That's the idea. You burn through the fishing line.
One more? Go ahead.
You mentioned SD cards that are reliable in space. What particular reason is that for?
So they're susceptible to damage from high energy particles, can lead to latch up or latch up, either damaging or non-damaging latch up. So
Would you experience the same with like an M.2 drive or an SSD or something?
yeah, they're both flash storage, so they're both susceptible. You can get different. This is something we're thinking about, so I don't have all the details.
I know you mentioned that, sorry.
No, you're good. But yeah, you'd still be susceptible. Although SD cards, I think, are kind of infamous for failing.
And I mean, to add insult to injury, I mean, it's, in general, you don't want to be pointing at something that's blasting X-rays out. That's what it is. So we're kind of rolling the dice. It's a risky mission. Hey,
Okay, let's give our speaker, thanks.
And I'll switch back to